Hi everyone, and it is closing talk for today. And hello, Dennis.
Hi.
Dennis is software enthusiast, and he will talk about Northern Lights today. So it will be a quite interesting talk. So you're welcome.
Okay, thank you. Hi and welcome in the end of this conference, which provide a great amount of very great content from people around the world. First of all, I'd like to say thank you to people who stand behind JFuture, people who committed themselves to make this event happening, especially in these uncertain times. As you noticed, lots of conferences being canceled, but still we're here together at JFuture, not just to promote ourselves and things we would speak about, but to stand for the Java community globally. To start, I'd like to introduce myself. My name is Dennis Makogon. I'm a principal member of technical staff, a member of Java Platform Group who is responsible for Java development at Oracle. With some of you, we have met in person around the world at the DevOps, the JFocus, JCons, and etc. So, as many of you, I'm a software engineer, meaning I write code for a living. Alongside with my work, on my spare time, I do a landscape photography as a hobby. But people on the internet call me like some kind of a pro-level landscaper. Well, maybe because one of my photos and like many more won very prestigious awards, and the latest one is the best drone photo of 2019. Maybe that's why, like, who knows? So what's this all about? Why you're here? So you're here to listen a quite interesting story of how my both skill sets in software development and professional landscape photography align together, and how such type of a collision turned into a great story of the Northern Lights hunt. So it's all started with a very simple question from a friend of mine: which country is the best to visit to witness the Northern Lights? And I was like, I was really uncertain on what to tell him. So I told him, pick the one you like the most. Go to Alaska, go to Svalbard, go to Iceland, Norway, Russia, Finland, Canada, Sweden, Greenland, north of Scotland, Faroe Islands, and Shetland Islands. If you haven't been to any of those, just decide upon your budget. But honestly, from the point of view of physics, the fact of the Northern Lights' presence up in the sky is a coincidence of multiple factors. So it's not just about the country. The Northern Lights phenomenon is a lovely dancing color waves. It's something that can be expressed, can be described as a set of measures. I ask myself whether I can answer my friend's question in a matter of software engineer with a certain background in data science and data analysis. From that moment, the answer to his question was nothing but a state of a system defined by a set of measures and expectation, and it can be expressed in like some kind of a mathematical form, and the result of this mathematical equation is the answer where to go. So I decided to write a theory, but I haven't been doing this since I graduated from university. So it might look a bit immature, but forgive me for that. I'm a software engineer, not really a scientist. So pardon. As you can see, this kind of a study is all about matching data, calculations, and some certain level of assumptions. But in order to make this case study, make this look in a better way, I decided to establish the Northern Lights Awards. And this is like an overall attempt to give an answer to the most simple enough form that can be consumed by non-technical people, because the whole theory of the Northern Lights requires a lot of knowledge about our sun, Earth, its magnetic fields, and a little bit in electrophysics. And this is how it's all started, the question and the Northern Lights Awards. So if you want to read the whole case study, the theory, the math behind that, just go to the GitHub. You can scan the QR code or just copy, just to follow this link on the slide. So I don't want to waste your time on this, but I'd like to highlight some key aspects of this case study. First of all, the Dark Sky API. This is a service that probably one of the best services, the weather services, that has a very simple JSON API. But the very best thing about this service is that it provides you the historical weather forecast, which is very crucial for weather predictions. And the best thing about that you basically pay per usage, but not for a monthly or yearly subscriptions. And the other part of my case study, the data for my case study, came from Helmholtz Center of Potsdam. This is like a huge university that provides you the data of magnetic field disturbance that being calculated all around polar circle. There's a base in Greenland, in Iceland, Norway, and as far as I can recall, in Canada. Yeah, that should be somewhere there. But in order to understand the whole case study, you need to basically get to understand three key aspects. The visibility of Northern Lights is very dependent on when, meaning the season matters, where, far north, so basically pretty close or far beyond the polar circle, up to the North Pole, and what other weather conditions. So basically, in order to witness the Northern Lights in the sky is supposed to be very clear. And by saying clear, there's a basic mathematical definition of what the visibility is and what they call a cloud coverage is supposed to be in percents, and the humidity and the temperature. It has to be very low. The humidity should be low. The cloud coverage in the sky should be like around 20% at maximum. In the best case, it should be around 0. And the visibility should be very, very straight, like up to 34 kilometers. That's what human eye can see, as far as I can recall. So these are three things we are not in control of, but as an engineer, so we do make decision which technologies to use to accomplish our tasks in a more comfortable form and in the most efficient way. But the term comfortable is kind of tricky here, as it actually declares a set of demands to the technology, and it has to comply 100% rather than just go above some abstract desired threshold. So let's speak a bit about those requirements. So the technology must be comfortable enough to work with sequences, with like data sequences. In the case study, each country is represented by a set of GPS locations. So the lowest number of GPS location per country is 9, and the maximum amount for, let's say, Iceland is 16. Each GPS location is described by 8 daily measures. Each daily measure is described by 3-hour weather forecast during autumn, winter, spring season. So it's like 226 days in a row. So it's like at the very minimum for a single GPS location, we need to do a minimum 3,000 calculations. So, and the amount of data is basically growing depending on what are the timeframes for the measures of the magnetic field disturbance. What are the we should basically extend the number of weather forecasts we'd like to obtain, and etc. So the amount of data is pretty significant for a single country. But the Helmholtz Center of Potsdam, they provide data starting from 1952 or like something about those years. So it's more like 70 years of actual measures. And in my case study, I did the research on all of those years to see which country was like the best from the very beginning of the measures that humanity actually made. So the other part is ability to build the reusable data pipelines and it's very crucial feature that my case study required. As a whole problem of solving algorithm is a set of sequence perceptrons that process multiple point-connected data sets from dark sky and Helmholtz Center of Potsdam. And basically, I need to get multiple inputs from various sources and then process them through perceptrons, and then finally get a statistics per country, per month, per hour, and per year. So since the case study is some sort of like a yearly challenge, the technology must be capable to run perceptrons in parallel. So the good thing is that the data is quite effectively splittable, because most of the times the data points in the case study are not dependent, and they can be executed. The processing against those data points can be executed in parallel. So technically speaking, each country can have its own pipeline, and that must be capable to run in parallel, parallel perceptrons for each GPS location, for each weather forecast on the location, for each hour for our measures that provided by the Helmholtz Center, and it should happen within autumn, spring, winter, and spring. So it's like the case study should go against 226 days, and those days can be parallel, because ideally what we'd like to have is to get the night hours, because the night hours is the time when you can actually see the northern lights, because at winter, the winter on the polar circle called polar winter, but the sun still goes up and just hangs just slightly above the horizon, so it's pretty light. So there's enough light to cause the very strong light pollution to shed the northern lights, and basically because they happen in 24 hours a day, because the sun is active like all the time. And the next one, like both Helmholtz Center data and Dark Sky API weather forecast, providing their data through API endpoints, the HTTP REST in particular. So in a context of parallel pipelines, it's very important to reduce the time on the blocking HTTP calls, ideally with some kind of a non-blocking technique. And the other thing is type system is not very crucial, but still quite important, as there are some data types that require additional manipulations. To be in particular, it's the data format, which is RFC 3339, which is not supported in various programming languages by default, but requires the additional software to basically parse the data into a native data format. So all I wanted here is to have a pretty good API, pretty good typing system. I want to have the same API to work with those types. So I just want to keep my hair that I'm kind of losing on my head and just work comfortably with the technology I would pick. And probably the winner is, yeah, it's Java. Java for data science. Don't you say you're not surprised, aren't you? There are multiple reasons why, and I'm gonna list out some of them that I found very critical for such tasks like my case study. So one of the greatest things that happened to Java Collections Framework was introduction of Streams API. So if you're not familiar with it, a stream doesn't store the data of a collection, but it just represents a pipeline of the perceptrons applied to each item of the collection. So all I had to do is to define, so with the Streams API, all I have to do is to define a set of perceptrons and a final collector that will basically represent the result of the case study for each country, for the months, for the year, and etc. The streams are really cool, like really, but it's not all. Streams API utilizes common fork join pool that run multiple units, multiple threads. So basically, Streams execution pipeline runs against fork join pool that runs multiple threads in a pool. So no matter what you do, as long as the data can be effectively distributed with the parallel. So, sorry, just 1 second. Oh, sorry. Yep, I think I'm back. So with the parallel streams, the workload can be divided with a configurable amount of threads that potentially can give you a boost in the performance. However, it might not be always like that. We all know that the runtime is fast, and the only thing that slows it down is our code. The effectiveness of the parallel execution can be expressed in a pretty simple way. As long as the computational cost of a single item processing through the whole data set is higher than the overall infrastructure provision overhead. So in this particular case, the amount of time and resources being spent to provision enough threads for the fork join pool, and the data set is effectively splittable, then the data processing should be considered to be executed in parallel. Let me explain this. I know it sounds very not very clear, but I'd like to explain this. So if an operation is so simple and its execution cost is lower than the overhead of the thread provisioning, then the data set must be very big, let's say big, really, to make the parallel processing worthless. It works also in the other direction as well. So if the computational cost of a single item processing is high and the data set is effectively splittable, then the size of the data set might not really matter in order to make the parallel execution worthless. So here's like a very simple example. If you want to perform an incremental operation against a data set that contains only integers, so in this case, the cost of incremental operation is very cheap comparing to the amount of resources and time required to provision the thread. So in this case, the size of the data set of integers is supposed to be very large in order to make the execution really worthless. And if you know that your single task within the parallel stream does a lot of operation, it does some outgoing IO input-output operations. So it may appear that this type of the stream execution against this with such a task against the data set, which might not be very big, is really considered as worthless because it actually can give you a boost in the performance comparing to the same stream, but the one that will not be executed in parallel. So, and I said multiple times the effectively splittable data. So as we all know, the most efficiently splittable collection type include array lists and hash maps. So the data structure that is considered as your data set, it should be efficiently splittable. It is considered as efficiently splittable if they internally support random access and efficient search operation, or ideally like both of them. So on the other side, if it takes longer to partition your data, then the process of parallel stream execution is considered as wasted. So the effort to run the parallel execution is wasted. And since my case study involves some IO operations, and as far as you know, there is an OpenJDK project called Project Blue that is the mission of it is to re-implement threads in the more efficient way, to basically reduce the amount of stack that each thread, the amount of memory that each thread occupies, and to replace the actual threads with virtual threads. And internally in JVM, there would be a carrier threads that will basically handle the execution of virtual threads. And the great thing about virtual threads that you basically can make the executor switch upon the IO operation. So basically, if within your parallel stream, if you do IO operation, you can avoid time wasting on the IO operation to reduce the time for another operation which is not IO bound, and then switch back when the IO operation finished or your HTTP request completed and you get a response for that. So the virtual thread may improve the whole thing about threads and application based on threads, and especially things that are related to the parallel streams and IO operations within those. So, and the other part of the streams that I like the most is their memory efficiency. So, as you know, a stream just stores its own metadata, and but it does store 0 bits of your data set. So basically, it's only aware of what to do, but not against which data set exactly. But there is only one moment when your application starts gaining in memory, is when your stream turns into a collection. So basically, when the whole pipeline of perceptrons completed its execution, and you want to collect them into a persistent type, like into a list or any other type. So that's the exact way, the exact moment when the application will gain some memory because you requested that. And I really like the way the Streams API being implemented. So depending on the task, So depending on the task you want to run against a data set through streams, a stream declaration could be potentially multiple forms of implementation. So just recall the way we write for each, how we write map and collection. So basically, that's the way you form a stream, and it's three states. The one when you have 0 output, so basically you perform any action against each element in for each loop. When you call methods like map, filter, flat, or etc., then the result of that is another string. And the collect method, when you call that, that's as I said, that's when you gain the memory. And I would say that for my case study, the reusability of streams is very important, because all I wanted to have a one stream, to have a pipeline of perceptrons defined in one stream and then reuse whenever I wanted to do this. So, but by design, a stream object is not reusable. So if you try to run the same stream pipeline again, an exception will be thrown saying that the stream is closed. However, there are some kind of a tricks that can help you to write reusable streams. So there are two things. You can do either through a function interface with the ability to parameterize your call, or through the supplier interface. But in this case, the stream will be reusable, but you have to bypass you have to pass down the collection itself. This is what you basically need to do this. So in my case study, which is kind of cool thing, I found out that Java is really great for multi-threaded data processing pipelines because, as I said, I had two different data sources that are not local. The data is coming from the internet, from the certain services. So yeah, Java is like, it's amazing. Just imagine that you have so many data points that require to be processed, mapped, filtered, collected at once, and things getting even better if you start taking into account that in my case study, data points are not dependent, meaning I can make the execution go in parallel without any problems, because parallel stream utilizes the fork-join pool to split the execution onto multiple threads and actually run your processing in parallel. Oh, and the ability to run asynchronous HTTP request with the JDK starting from release number 11 is really amazing, because you can actually save some time on the execution as well by letting the rest of the task utilize the time that being the time being spent for the other execution. Oh, and it started with a very simple question, like, which country is the best? So after a month, I gave my friend an answer. So far, the Finland is the best one by number of days. A few years ago, Iceland was the #1, but now it sits in second place. Sorry, Java Zone folks, really sorry. Norway sits on the third place. Although I'm in love with Tromsø, Senja, and Lofoten Islands, and Sweden is like the last one, because there are like too few places to go to see Northern Lights, too few days to be suitable, to have suitable conditions to witness the aurora because of the weather, and that's pretty much it. I hope you enjoyed that. So if you have time and you have a very good skills and things you do, just try to apply your professional skills into your hobby. I bet like lots of you have been doing this, but try to find a very cool way to show your professional skills to people who is not involved in tech. So this is like very fun thing, and I will remain this kind of a yearly award run through year 2020 and go beyond that. So let's see how it will goes. I bet in this time on the lockdown, people will be very curious on what's the best country to go to see the Northern Lights in this year, although we will be all sitting at home. Sorry for that. And we're probably done. Hope you find this talk interesting, even though it wasn't packed with lots of technical stuff. Anyways, thank you for listening. I really hope you have questions. I want to say thank you to JFuture folks who made this conference happen. I hope we're gonna see each other next year. Thanks.